All right, we're starting part 3 with the Desmos. Peek at this graph. There it goes through 243, just like I promised you. And there's the red one is the function itself, and we can see that it's always increasing except for at its 0, which is -3/2. Also, what's pretty cool about Desmos is that I can graph the derivative function without much hassle, um, and I can see the derivative function is this blue one, and it's always positive. It's always positive except for 0 at that one spot, just like we knew it was going to happen. How did I do the derivative? Um, Basically, what I did is I copied that, and then I went to functions, miscellaneous, and one of them is the derivative. Bam. Just like that, it graphs the derivative. So that's kind of nice, especially if you want to do test points. My test point was -2. And notice there, my test point of -2, I could just put in -2 or anywhere, right? And or just graph it and see where it's positive or negative, the first derivative. It's kind of a nice cheatsy check. Can we use Desmos on the test? Absolutely not. You have to be able to do this using algebra, but certainly it'll help you have confidence in your algebra work. All right, where are we? I think we got one more example to go. And it's a rational function. No, no, no. One more example. Oh, the one example here, I'm going to have to copy this onto a new page. We're getting a little bit cramped here. Copy. Put on the new page. Here we go. So what's the idea? Increasing and decreasing. Well, we know we're going to have to take the first derivative and set it equal to 0. No, no getting around it. Let's find the first derivative. So that's the plan. Pen's not working. Oh, no, there it goes. Seems to be a theme, doesn't it, in this calculus deal, is taking the first derivative and setting it equal to 0. All right, well, let's do that. Looks like a quotient rule to me, although some of you may prefer to write this as a product rule with a negative exponent. I'm going to leave it like this. Take the derivative of the top, write down the bottom, subtract, write down the top. Derivative of the bottom is a chain rule. Be careful, right? Chain rule, 2 comes down, left inside, and then the 1 derivative of the inside is just 1, so that's all good. And this looks terrible, but it'll get better. All over the bottom squared. No, I'm going to be a little tricksy here because I see a common factor. You see the common factor of x minus 2? And you've maybe noticed that this always happens. Rational functions, we'll see a pattern in a second, but I take this out. What's left is, was left from the first term. Subtract what was left from the second term is just 2x all over x minus 2 all squared. Then notice what I can do is I can cancel out, darn it, rest all, making mistakes all over the place. Remember the bottom squared. So this is actually x to the 2 minus x to the exponent 4. Sorry about that. But now I can cancel one of those factors, right? This is actually x minus 2 cubed on the bottom. And so this, and you've probably noticed that this always happens. When I'm doing a rational function, the exponent on the bottom goes down by 1 at a time. Hopefully you've noticed that. I wouldn't remember it as a rule, just observe it when it happens and know that you're on the right track. Clean up the stuff inside the brackets. I've got negative x minus 2. Checking my notes here to make sure I got the right derivative. Yep, looks good. And so now I'm going to set this equal to 0. All right. Then I need to remember how to solve rational inequalities or rational equations. Where did I get the 3 from? I should have just quit while I was ahead here. You're snickering to yourself out there in computer land, but it's no fun making mistakes. Um, Hopefully it caught that one as well. X minus 2 on the bottom. And can I cancel this? No, because of this minus, right? They're not the same bracket. But this isn't so bad because I remember from functions how to solve rational equations. As long as x isn't 2, I can multiply by x minus 2, and I get 0 equals negative x minus 2, x equals minus 2. And so that's the spot where f at x is equal to 0. F prime at x, right? So if we do the sign chart, sign chart, sign chart, sign chart, there's f prime at x. Remember, though, when I was solving rational inequalities in functions class, we also had to put the spots where it was undefined on there because we could have a sign change on the either side of the spot where the derivative is undefined. So we do have to put on there. We need to include discontinuities. And the spot where it's 0, right? F prime at x is 0 there. And then we can check signs. So what do we got? We got I'm going to copy this back out just so I have a decent copy of it here. This is what I'm checking out for my test points. Like in here, what would I have? Well, for x equals minus 3, I'd have a negative, and then negative 2. So this would be, notice this would be positive then, right? This would be a positive number. This negative of negative 3 minus 2. If you can't see that, put it into your calculator. And then on the bottom, I'd have a negative 5 in this case, cubed, which altogether is, what's that? That's a positive, negative, right? So here it's negative. And now you kind of understand why, even though we did the sketches in function to get the sign chart, it's important in calculus, isn't it? So what's in between there? My favorite x equals 0 test point. In here, rough. This is all rough work, right? We can do this in the margin. But then I'd have a negative on the top because this is 0 over a negative cubed, which is going to be a positive altogether. So it's positive here. And then on this side, x equals 3, positive 3 maybe. I'm going to have a negative on the top and then a positive cubed on the bottom, which is going to make that negative overall. And so from here, I can pick off where it's increasing and decreasing, right? From this, it tells me that this is where it's decreasing, increasing, decreasing, right? So my conclusion, I'm looking for some spots to make some conclusions now from my sign chart. So f at x is increasing where the first derivative is positive. Notice I don't include the endpoints, and I don't include the spots where I have a minimum or a maximum, and decreasing elsewhere. X is less than negative 2, together with x is greater than 2, right? Yeah, that's right. And then notice that this also tells us decreasing, 0, increasing. We've got a f has a minimum at x equals minus 2. And just for funsies, why don't we just go right to Desmos and pound that in and see what this thing looks like? Yeah, no. We have, what was the function? It was x over x minus 2 all squared. Hard to see what's going on because we're so zoomed out. Let's make this maybe minus 10 to 10 hopefully we can see. Where do we say the minimum was? Let's zoom in even closer. I think we said the minimum was at x equals -2, and of course Desmos points these things out to us. But let's zoom in there just so we have an idea. We need smaller y values, maybe from minus 0.5 to 0.2 or something like that. Ah, there I can see the curve in the graph. Yep, there's a minimum at -2. And I could use my functions knowledge, my MCV4U knowledge to get the sketch, but there's the sketch using Desmos. A little bit cheatsy, but certainly I probably could have used my functions knowledge to help me out getting a sketch. That's it for the lesson. I want to mention something though. If you've looked at the CEMC courseware, there's a couple of lessons that come before the stuff that we're talking about here, and they're lessons on the extreme value theorem and the mean value theorem. These two things are very important calculus topics that are in AP Advanced Placement Calculus, and in your first year calculus class next year will have these on the in the course as well. But it's not in MCV4U. So there are lessons in CMC and CEMC. If you're interested, please watch them. It's, you know, interesting material, difficult material, but these two theorems actually lead to what we were talking about today, the increasing function theorem. Okay, that's all I have to say about that. Have fun with your homework.